Section 4.2 is really about a big theorem in calculus called the mean value theorem. And we're going to start our discussion, though, talking about Rolle's theorem. Rolle's theorem is actually a corollary of the mean value theorem. That means that it's a result that follows directly from the theorem. Really, Rolle's theorem is a special case of the mean value theorem. That's one way that you can think about it. And as we are working these problems, you'll see this when we start working it. But a lot of the reason that we are doing these is not just because the mean value theorem has a lot of applications in its own right, which it absolutely does. But the other goal in talking about these theorems is to make sure that you understand a mathematical theorem and how to read it and how to check the hypotheses and the conclusion. So definitely, it's not just about getting the answer. It's also about understanding the statement of the theorem. So don't hesitate to ask as we go along if you don't know what I mean by that. All right, but you can read the statement of the theorem there. It says, Rolle's theorem says that if f is a continuous function on a closed interval and it's differentiable on the open interval from a to b, and if f of a equals f of b, then there exists this number c in the interval such that f prime of c equals 0. Now, we can read those words, but it may not make much sense to you. Like, what is it really saying? So I'm going to show you an example of what it is really saying. It's easier to see that if we draw a picture. So I'm going to sketch a little diagram right here. And I like to have people kind of do that on your own too, and not just look at mine. That's a little bit harder, okay, when we're kind of doing it online. But I still want you to give it a try. But all right, so let's talk about what has to happen when we draw our picture. First of all, when we are talking about the theorem, before we can draw a conclusion, the hypotheses of the theorem have to be true. So the hypotheses are the things that have to be satisfied before you can draw the conclusion. So in this problem, notice that before we can use Rolle's theorem, we have to have a continuous function on a closed interval. So that's one of the hypotheses of Rolle's theorem. I'm going to number them. So the first hypothesis that I see is that f is continuous on the closed interval from a to b. Okay, now I want you to help me out because I see another one there. What else has to be true before we can use the theorem? What's a second hypothesis of Rolle's theorem? It has to be differentiable. So f has to be differentiable on, notice, the open interval from a to b. So do you notice that? It has to be continuous at the endpoint, but it does not necessarily have to be differentiable at the endpoint. Okay, now we want to draw a conclusion, but there's one other thing that has to be true. Does anyone see it? What is the other hypothesis that has to be true? Yeah, f of a has to be equal to f of b. Okay, so those are the three things that have to be true before we can draw a conclusion. The conclusion is the part that comes after the then. Okay, so if all of those things are true, then the conclusion is there exists at least one number. So I'm just going to write that out. There is at least one number c. That should say 1c, not once, sorry. At least one value of c in the interval from a to b such that f prime of c equals 0. Okay, so that's what the theorem says. So let's draw a picture. So we have to make the hypotheses true. So f has to be continuous on an open interval, on a closed interval. So notice I'm just making a closed interval. So put that a and b anywhere you want. And I'm going to draw a curve. It's continuous, so that means when I draw it, I can't, you know, lift my pencil. It's differentiable, which means when we draw it, there are no sharp points. F of A has to be equal to F of B. It doesn't really matter where you put F of A and F of B. I'm going to put it right here. So this is the point A, F of A. So what I know is that F of B has to be the same. So this is F of A. The y coordinates match. That's what the third part says. All right. So now what I would like for you to do, really do this, okay? On your paper, can you draw a continuous differentiable function that goes from this point on the left to this point on the right? Now, one way to do it is draw it straight across, and that would definitely work. Okay, but let's make it a little more interesting. So don't just draw a horizontal line, although that would work. So let me know in the chat window when you have some function drawn where you didn't lift your pencil and you don't have any sharp points between A and B. So just let me know in the chat window, I have one. And so I see 3 or 4 of you have one. Okay, great. Yeah, so keep drawing yours. Now I'm going to draw one on my paper, but don't erase yours and make yours match mine. Okay, use yours because that's really the point. The theorem says that it doesn't matter how you drew it. So I just totally made that up, right? So I was just trying to draw some kind of smooth curve. Okay, but what the theorem says is that whatever yours look like, even though it may have looked very different than mine, if you made all of those hypotheses true, there has to be at least one place in that interval where your derivative is equal to 0. And remember, if the derivative is 0, that means you have a horizontal tangent line. Now mine, it just so happens that it looks like I have 2 places, and so that's not guaranteed. What the theorem says is that you have to have at least one. So it looks like I would have one here and another one here. So does everyone see that on your paper? Is there at least one spot in your curve where you have a horizontal tangent line? Yeah, that's what Rolle's theorem says. Okay, so now let's see if we can apply that to the function. But any questions or comments about what we have set up above about the statement of the theorem? Okay, so now for our problem, it's going to look like you see on your paper. You're going to be given a function like f of x equals sine 2x in a closed interval. And the question says, first of all, determine whether Rolle's theorem applies. And if so, then find the values guaranteed by the theorem. Don't gloss over the first part because that's one of the parts that I'm really testing for. Again, it's not just about getting an answer. When it says determine whether Rolle's theorem applies, that means that you need to check the hypotheses of the theorem. So I'm numbering them just like I did up above. Okay, if we want to know if the theorem applies, we have to check, first of all, is f, so in our f this time is sine 2x, continuous on the interval from 0 to pi over 2? That's the question. Okay. And notice I'm just taking sine of 2x. Those trig functions were in our list back in section 2.6 or 2.4, 2.5, somewhere along that back there, the very first week of class. We had a list of functions that we could say are continuous, and sine was definitely on that list. Okay, so there's not a lot of work to show me there. You're just showing me that you checked. Because we know sine 2x is defined for all real numbers, so we know there's no problem. Okay. And so if that were a grade scope problem, yeah, you could just write down kind of what I am writing is trying to model for you what I want to see. I just want to see that you checked that it's continuous. Number 2 wants to know if it's differentiable. To know if a function is differentiable means you're going to have to take the derivative, okay? So the question is f differentiable on the interval from a to b? And notice it's an open interval. That's the question. And so to answer that question, we need to find the derivative. When I take the derivative of sine 2x, what rule do we have to use? Yeah, that's the chain rule. So we take the derivative of the outside function times the derivative of the inside function. And to be differentiable means that that derivative is defined everywhere on that interval. So is our derivative defined on the open interval from 0 to pi over 2? Is that true? Yes, good. Okay, so that means that our function is differentiable on that interval. Okay, so then the third thing we have to check is to see if f of a is equal to f of b. So in our problem, notice that our a is 0 and our b is pi over 2. And so we need to check, are those two things equal? And we decide if they are equal by plugging them in. So we're going to plug those values into our function. F of 0 would be sine of 0. F of pi over 2 would be sine of pi. Notice I'm plugging them back into my original function. 2 times pi over 2 is pi. And sine of 0 is 0, sine of pi is 0, so those are equal. So any questions about that before we go on? Okay, so all of that means that the theorem applies. We can use it. So that's the part that you have to do before you actually answer the second part of the question, which is, if all of those things are true, then find the points guaranteed by the theorem. Okay, so now we're using the conclusion of the theorem. And the conclusion says that there has to be at least one place where the derivative is equal to 0 on that interval. So we need to find that value of c. So notice we've already found the derivative right here. So what we are saying is that if we set that derivative is equal to 0, that it will have at least one solution in our interval. So now I'm solving this equation to find the solutions in our interval. So if I divide both sides by 2, we would have cosine of 2x equals 0. So now I'm thinking about my unit circle, right? Cosine of something equals 0. Help me out. Where is cosine equal to 0? Cosine of what equals 0? Yeah, pi over 2. Good. Someone said 3 pi over 2. Good. So that means 2x could be pi over 2. 2x could be 3 pi over 2. And depending on what our interval is, we might have to keep going around the circle. So we know there are infinitely many answers. Those are the two that we get between 0 and 2 pi. Notice the interval we are given is between 0 and pi over 2. So as long as we find all of the solutions in that interval, we're good. So I'm going to take this first one. If 2x equals pi over 2, if I divide by 2, what's pi over 2 divided by 2? Or pi over 2 times 1/2, if you'd rather think about it that way. We would get x equals what? Pi over 4. Good. Notice if I do the same thing to this one, multiply both sides times 1/2, I would get x equals 3 pi over 4. And notice as soon as I do that, that I'm out of my interval, because here is pi over 2, 0 to pi over 2, 3 pi over 4 is in quadrant 2. So the only one in our interval is pi over 4. So notice that's the one I called C. It is true that x equals 3 pi over 4 is a solution to this equation, but it's not the solution that's guaranteed by Rolle's theorem. Rolle's theorem says there's at least one solution that's actually inside your interval from 0 to pi over 2. So any questions about that one before we try another one? Okay, so we'll stop there. Let's take a little break. So get up and stretch out, and then we will come back and do the next example about Rolle's theorem and talk about mean value theorem. So come back in 5 minutes or so. Hello, I'm back. If you let me know if you can hear me, then I know you're back. Thank you. So, any questions at all about that first example before we go on to the next example? Okay, so it's going to be same idea. So the directions say determine whether Rolle's theorem applies, and if it does, then find the values guaranteed by the theorem. Okay, so just like before, make sure you check the hypotheses. So first thing we need to ask ourselves is F continuous on the closed interval from -1 to 1? And if it helps you, you can rewrite that x to the -3rd. Remember, that's the cube root of x squared, if that helps you think about it. Okay, so what do you think? Is that function continuous on that interval? Yeah, it's continuous there. It's defined everywhere on that interval. We don't have any fractions. We don't have to worry about the denominator being equal to 0. We're taking a cube root, so we don't have to worry about that radical not being defined. Everything's fine, so that's good. So the next thing that we have to check is to see if f is differentiable on the open interval from -1 to 1. And remember, to figure out if a function is differentiable means, is the derivative defined? That's what it means to be differentiable. So we need to actually find the derivative. So if I find the derivative of that function, the derivative of 1 is 0, minus, drop that exponent down front. So it looks like this. Then I would rewrite it so it doesn't have a negative exponent. 2/3 minus 1 is -1/3, right? That should be a -1/3. I meant to subtract 1 from that exponent. So where is that derivative not defined? Yeah, it's not defined at 0, so that means that it is not differentiable at x equals 0. And notice that x equals 0 is in our interval from -1 to 1. So that means that if it's not differentiable on that interval, Rolle's theorem does not apply. Which means that we can stop. We don't have any other work to do. Okay, just to note that that does not mean that there's not somewhere where that derivative is equal to 0, even on that interval. But what it does tell us is that we could not get that value by applying Rolle's theorem. Rolle's theorem only guarantees that there's a place in that interval where the derivative is equal to 0 if those hypotheses are all true. Okay, so any questions about that before we move on to the mean value theorem? Okay, then let's talk about the mean value theorem. So here's the statement of the theorem. So it's going to look very much like what happened when we started talking about Rolle's theorem. Notice that we have to have a continuous function on a closed interval, and our function has to be differentiable on the open interval from a to b. If that happens, then there is at least one number c where f prime of c, as you can see it there, is equal to f of b minus f of a over b minus a. Okay, so let's draw a picture so we can make sense of what's really going on there. So just like before, we are going to pick out the hypotheses of the mean value theorem. So what are the things that have to be true before we can use the theorem? Well, first of all, notice we have to have a continuous function on a closed interval, AB. And our function has to be differentiable on the open interval from A to B. But notice there's no third condition. So do you see Rolle's theorem has an extra condition? That's why I said it was a special case of the mean value theorem. So the mean value theorem is a more general theorem. So it applies to more functions in more situations. So we only have to have those two hypotheses that are satisfied. And if those two are satisfied, then the mean value theorem says, you can see it there is at least one number. I'm going to use this symbol. Some of you who go on and take more math classes will see that anyway, so I'm going to go ahead and use it. That big backward E stands for there exist. So there exists at least one number C in the interval from A to B. So that means C is an element of that interval. So C is inside that interval, such that, and you can write it out in words if you would rather, but when you see a backwards epsilon, when you are using mathematical theorems, you always read that as such that. That's an abbreviation for such that. So there exists some C in the interval AB such that f prime of C is equal to f of B minus f of A over B minus A. And that kind of looks like a lot of mumbo jumbo again until we look at a picture so you can see what it's really saying. So we're going to draw a picture again. Okay. Just like before, I want to make sure the hypotheses are satisfied. So I need to draw a continuous function on the interval from A to B. So between A and B, I'm never going to lift my pencil. It has to be differentiable, which means it does not have any sharp points. But notice we don't have that extra condition where the f of A has to be equal to f of B. So I'm going to intentionally make them not in the same place. So I'm going to just put them here, but you can put them both above the axis or both below the axis. It doesn't matter where you put them. That's kind of the point. So, and just like before, I want everyone to draw a picture on your paper, draw a curve that connects those dots. You could have put the dots somewhere other than where I put them. That's fine. But everybody draw us a nice smooth curve between those points. And let me know in the chat window when you have one, because I don't want you to think that it has to look just like mine. So Jamie has one, Garrett has one. Thank you guys. Yeah, thank you. All right, so, and I'm just going to draw one in here. So it looks like I'm pretty boring. Mine looks quite a bit like the one I did last time, but that's all right. Yeah. So the point is it doesn't really matter what it looks like. Okay. Other than it has to be a function, it has to pass the vertical line test. You can't lift your pencil and no sharp points. Those are the conditions. All right, so now for the conclusion of the theorem. It says there has to be some point C where the derivative of C at that point, which means the slope of the tangent line, right? So there's some place where the slope of the tangent line is equal to, let's write out these points. The x coordinate here is A, so the y coordinate is f of A. Here, the x coordinate is B, so the y coordinate is f of B. So notice this f of B minus f of A over B minus A. That is actually just the slope of the line that goes through those points. So if I have, whoops, if I have a line, let's see if I can. So here is a line, right, that goes through those 2 points. So pretend it actually, I'll make this dot at the top bigger, right? So I want it to go through those points. And notice if I ask you to find the slope of that line, it would be the change in y over the change in x. So what the mean value theorem says then is there is at least one spot on this curve. So I'm trying to eyeball it. It looks to me like mine might be right here, where if I draw the tangent line at that point, I get the same slope. So, or in other words, it's parallel. I should have made my, here, I'm going to make my program, I'm going to hold it there so it can make a line. So maybe I can shift it a little bit if it doesn't look parallel. So this is the point C. That is guaranteed by the mean value theorem. So you do that on your paper. Like if you draw the line that goes through those two original points, is there some point on your curve where you could draw a tangent line that would be parallel to that original line? Let me know if it looks like you could do that on your paper. Yeah, so Garrett sees how he can do it. Yeah, so that's what the mean value theorem says, is that there has to be a place, okay, where those lines would actually be parallel. Okay, so if we think about it from a physics standpoint, this is what the mean value theorem really says. Okay? And you'll see why it's called the mean value theorem, I think, if I say it this way. If I tell you that I had to go to Little Rock on Saturday, and I drove an average of 72 miles per hour. Okay, so, but when I started at home, I was going 0 miles per hour, right? And when I got to Little Rock and stopped, I was going 0. So this is kind of like Rolle's theorem too. But if my average was 72 miles per hour, what the mean value theorem says is there had to have been at least one spot between here and Little Rock when I was going exactly 72 miles per hour. There's no way that 72 miles per hour could have been my average if I didn't actually go 72 miles per hour in at least one spot between here and there. Does that make sense to you, what I'm saying? Yeah, that's what the mean value theorem says physically. Okay, so there has to be at least one place where you hit your average. That's how it got its name, mean value theorem. All right, but now let's talk about how to use it in context of our functions. So just like when you use Rolle's theorem, there's really two parts to using the mean value theorem. One is understanding the mathematical theorem, being able to pick out the hypotheses in the conclusion, and the other one is then finding what the theorem tells us we can find. So when the problem says determine whether the mean value theorem applies, don't ignore that part. That's a big part of that question. So to decide if the mean value theorem applies means check the hypotheses of the theorem. And at least for the mean value theorem, we only have to check two. First, we have to check to see, is our function continuous? Natural log 2x. So is this function continuous on the interval from 1 to e? That's the question. Well, we know that the domain of this function, right, you guys told me earlier, right, we can only take natural log of positive numbers. The domain of that function is from 0 to infinity. So that function would not be continuous at 0, but notice that's not in our interval. And in fact, the logarithms were in our list of functions that were continuous everywhere they are defined. And our function is defined on that interval. So we can just say it's continuous. So again, there's not any work to show me other than just writing it down and telling me that you checked. The other thing we have to check is to see if f is f differentiable, okay, on the open interval from 1 to e. And anytime we want to know if a function is differentiable, we take the derivative. So when we take the derivative of the natural log of 2x, what rule do I need to use? Yeah, chain rule. So we say 1 over 2x times the derivative of the inside, so we get 1 over x. And for a function to be differentiable means that its derivative is defined. We know this derivative is not defined at x equals 0, but again, notice that's not in our interval. So it is differentiable on the interval from 1 to e. And you can write a little note there saying it's not defined at 0. That's not in our interval, so we don't have to worry about it. So any questions about the hypotheses before we go on to the conclusion? Okay, so the conclusion of the theorem says there is at least one place where the derivative, notice that the derivative of our function is 1 over x. Notice I didn't call it c yet. Sometimes if you look at an example in my math lab, they may actually put a c there, but I may get answers that are not in our interval. I'm only going to call the ones that are guaranteed by the theorem c. So I'm just going to leave that derivative as 1 over x is equal to f of b minus f of a. In my problem, what is my b? So here, this is what the mean value theorem says. In my problem, what is b equal to? Yeah, that's e. This is your interval, so this is your a and b. So f of b would be f of e minus f of a over b minus a. And what the mean value theorem says is there will be at least one solution to that equation that is inside our interval. So we're going to find it. But any questions about how I got that before we go on? Okay, so to find f of e, remember this is our function. So f of e would be the natural log of 2e minus f of 1 and what is the natural log of 1? Yeah, natural log of 1 is 0 because e to the 0 is equal to 1. So we have 1 over x I'm trying to write, sorry. 1 over x is equal to the natural log of 2e over e minus 1. So you can think about that as cross multiplying if you want. I just have one fraction on each side. So x is equal to e minus 1 over the natural log of 2e. So I only got one solution to that. So I know that has to be the solution guaranteed by the mean value theorem. If you want to approximate that in your calculator just so you can make sure it's in that interval, so if you made a mistake, then do that. But since the mean value theorem guarantees us that there is a solution in our interval, and that's the only solution I got, I know it has to be in that interval, unless we made an arithmetic mistake. So that's the value of C guaranteed by the mean value theorem. So any questions at all about that? Just a reminder to not approximate that answer when you write it down. If you want to, approximate it just so you get a feel for how big it is, then that's okay. But don't write down a decimal for your answer unless the problem actually said to round or approximate. Okay, so we're going to try another one if there are no questions about this one. Okay, so the next one on your paper then. So same idea. The question says determine whether the mean value theorem applies, and if it does, then find the values of C guaranteed by the theorem. So first we'll check the hypotheses. Are those true? So is F continuous on the interval from 1 to 3? Sometimes when you work these, the answer to that question is going to be no. So don't just gloss over that. In particular, when I look at this function, help me out. If I just ask you, where is that function not continuous? Can you tell me where it's not continuous? Where is this function f of x equals x plus 1 over x? Where is it not continuous? Yeah, when x equals 0. But notice that's not in our interval. So it is continuous on this interval. So we're good. So then we ask, is f differentiable on the open interval? And to answer that question, we need to find the derivative. So you guys help me out this time. What is the derivative of x plus 1 over x? Good, Jamie. The derivative of x is 1. The derivative of 1 over x is minus 1 over x squared. So I'm going to get common denominator and just rewrote it so it's easier for me to look at. Okay, there's our derivative. So does our derivative exist on the interval from 1 to 3? What about everyone else? Does anyone have a question about the differentiability part? But notice it's not differentiable at x equals 0 again. Good question, Garrett. A function is differentiable as long as its derivative exists. So in this one, notice the derivative does not exist when x equals 0. So this function would not be differentiable at x equals 0. But notice that is not in our interval, so that's okay. Notice x equals 0 is not in the domain of our function. Okay. But to be differentiable means that the derivative exists. Okay, so but if we know those things are true, then we know that we can apply the mean value theorem. So the mean value theorem says there's at least one place where the derivative, which we already found, right? So notice I just copied that down, where the derivative is equal to, can you all help me out this time? What should I write on the right-hand side? Don't give it to me simplified because I want to make sure everyone sees how we got it. How do you think about it to get the right-hand side? The mean value theorem says that the derivative is equal to what? Can anyone help me out? What should I put on the right-hand side there? Look back at the problem we just did if you need to. So because now we're using the conclusion of the theorem, that's what we're doing. Yeah, was someone going to ask me a question? Go ahead. Good. Daniel's telling us we get f of 3 minus f of 1. That's exactly right. Any questions at all about where that came from? Let me hear from everyone. Okay, you should see a poll on your screen. So glance up and respond to my poll for me. Okay, so what about everyone else? Has everyone who's here had a chance to respond? Okay, so I see that someone has a question, so I'm going to hang out here just a second to give you a chance to figure out what you want to ask. So when you find your question, go ahead and type it in or unmute. Or if you found the answer yourself, just let me know that too. Okay, so whoever said that you had a question, can you let me know if you still have a question? Okay, so if you do still have a question, feel free to jump in there. All right, so once we know that we have a solution to that equation, we just need to find out what f of 3 is. So notice I'm going back to my problem. When I find f of 3, that would be 3 plus 1/3 minus f of 1. Notice if we plug in 1, so I'm going to simplify that fraction. And I want that to look as nice as possible. Okay. So 3 minus 2, notice that's 1 plus 1/3. So it looks like I have 4/3 over 2. And let's make that look a little better. 4/3 divided by 2 would be 2/3. Now it'll be easier for us to solve. So any questions about what I did there? Okay, so I'm just going to cross multiply. So I have 2x squared equals 3x squared minus 3. So I'm going to subtract 3x squared from both sides and then divide by -1. So it looks like I will end up with x squared is equal to 3. So I get x is plus or minus the square root of 3. So we still need to pick out the answer to our problem, but any questions about solving that equation before we do that? Okay, so the question says, what is the value guaranteed by the mean value theorem? So can you all help me out? Which one of those is guaranteed by the mean value theorem? Yeah, positive square root of 3. Because notice our interval is just from 1 to 3. So we know it has to be positive. So there were two solutions to that equation. Okay, but only one of them is actually in our interval. So any questions at all about that example? Okay, so we are going to stop with that one. So if you don't have any other questions, feel free to sign off and use this little extra time to get a jump start on your homework for this section. But if anyone needs extra help with anything, please stay. So we have lots of class time left, and I want to help you if you have questions. So don't be shy about hanging around, and I will look at any problems that you want us to look at together, where they were on the quiz or homework or anything else. But if you sign off, have a great day. You're welcome. Thank you all for being here today.